Any other nominations? E has been nominated. Anybody else? Okay, should we have them do a cage fight? See. E or F? Oh, sorry, F wins. Okay. All right, what is F?
That was the part of the plane 2x plus 3y plus 4z equals 5. That's inside y squared plus z squared equals 6.
Okay. So, part of the plane 2x.
2x plus 3y plus 4z equals 5. And then
Inside
y squared plus z squared equals 60.
Okay. Let's turn them in. And then I'll go over it. Don't worry, I won't grade that one, okay?
I think for recitation, kind of is it
What's that?
Like did it matter what time you passed it to?
Oh.
Or is it the same thing?
Yeah, I like recitation. Okay, so the fact that it's restricted to, did I turn this on? Yeah. The fact that it's restricted to inside y squared plus z squared equals 16, that might make you think that you're going to use some kind of theta or some rotational, but that's just the restriction. So really what you got to think about here is that the points are on the plane, okay? So the points are on the plane so that we want to parameterize. So how would you parameterize a plane? It's the easiest way.
Like set x equals something?
Yeah, just, yes, solve for z. So z is going to be, what, 5/4 minus a half x minus 3/4 y. So one way to do this that's totally legit is just to do x and y as your free variables, right? And then given a set of order pairs x and y, z is always determined by this, right? So that's your z component. And then the qualification is inside y squared plus z squared equals 16. So what does that mean? Y squared plus z squared equals 16. It's like this, right? Okay, so yeah, so there needs to be some coherence here between what we do and what our I'm trying to think here.
Maybe set x equals
What's that?
maybe set x equal to like
Right. That's what you want to do. Okay, thank you. So because of the restriction on something along the x-axis between y squared and z squared, we want it, so rather than use the parameters x and y, you want to use the parameters y and z. Is that what you're going to say too?
yes.
Yeah, that's what you want to do here. So for this one, instead of solving for z, we want to solve for x. So we want our two parameters to be y and z. And then what is x? So 5/2 minus 3/2 y minus 2z. Always just not enough room. Minus 2z y. Okay, there we go. So now, and then we can restrict, because y and z are parameters, we can say y squared plus z squared, what, less than or equal to, or less than 16. Is there an example like that in the video where I changed it up and used different parameters? There was? Okay. Instead of x and y and solving for z. So because of this restriction, what makes sense is then to solve for x. Use y and z as your free variables, and then x depends on what you choose for y and z. Okay, and so then this could also be written in a polar form. So now we have it this way. We could also do polar form. And so then what would our two variables be? Yeah, so it's going to be, this plane inside of a plane cutting through a cylinder, like a circular cylinder, is going to result in an elliptical shape, right? So we could also, we could also have parameters r and theta. And so then y would be, so if we have y like this and z like this, so then what would y be in terms of r and theta? R cosine, because y is the horizontal component. So we could do r cosine theta, and then z would be r sine theta. And then what would x be? 5 halves minus 3 halves. Watch, again, I'm not got enough room. I'm doing my best. R cosine theta minus 2r sine theta. Right. Okay, and then what would the restriction be then? If it's y squared plus z squared is less than or equal to 16, that's the same as r is less than 4, right? I shouldn't have done that. I'm having a bad day. Yeah.
Did you specify the theta to 0 to 9?
Yes, right. Exactly. So r is between, and then theta from 0 to 2 pi.
Does it have to be strictly less than, or does it not matter that much?
Well, if it says inside, if it's strictly said inside, then that would not include the actual boundary. So then that would be strictly less than. Okay, so does that? So there's the final answer. So two different ways to do this. You could do it parameterize y and z, and then your x solve for x in terms of y and z, or you could use r and theta. Then you'd have r cosine theta for y, r sine theta for z, and then that expression with those plugged in, and then our restriction would just be r less than 4, and 0 and theta between 0 and 2 pi. Okay. Other questions on parameterizing surfaces? Okay, so we're talking about curl. Let's pick it up where we left off last time. So these last 2 weeks are going to get harder, as I promised. So we're talking about curl in R3. So curl in R3 means that you have kind of 3 components of rotation. At any point in an R3 vector field, there's going to be 3 components of rotation we're going to separate it out into. So like rotation in xy plane, rotation in yz plane, and rotation in xz plane. Okay? So this is showing how we would derive the rotation in the yz plane. So I have a little element here, 3-dimensional element. So this is like our dx right here. So dy, dz, dx. Okay? And so focusing in on just the rotation in the yz direction, rotational rate, it's just the same thing we did before. So we're going to say, so for a change in z, what's going to, as z changes, what's going to contribute to rotation in the yz plane? Put dx here. So for a change in z, we're looking at how the vector changes this way. So what's going to contribute to rotation with respect to z changing? The y components, the red ones, or the x components, the z components, the red ones, or the y components, the green ones? The green ones, right? So the green ones are going to, so that change in, and so that is what? This is P, say P sub B, and P sub T. So the change in P, is that right? No, it's not right. It's Q, because we're in the y direction. Told you I'm not having a good day. So yeah, so Watch out for my mistakes, especially today. Okay, so the change in Q, because that's the y component of our vectors, with respect to z is what's going to contribute to rotation in the yz plane. So for a little change, so what is the change in Q here? So if the QB is this vector and QT is this vector, then what is dq? What is dq? If QB is this vector here and QT is that vector there, then what is dq? What do we mean by dq then? It's not a rate, right? dq is not a rate. So if this is our starting Q down here, and we have a change in Q to get this Q up here.
So it's on
Right, and what would that be in this case?
QT, so it's just a change in Q.
Yeah, and so it'd be what? It'd be a vector in this direction. So which direction would it be? So if this is QB and this is QT, would it be to the right or to the left?
To the right.
To the right because?
There's more I apologize, I can't say it precisely. The top one's bigger and this small.
QT is bigger, right? QT is bigger to the right than QB is to the right. So dq is like however much, if this was QB like this, then right, that's dq right there. Do you see that? That vector right there is dq. If this much of it's QB, then dq is like this. And so we have a little change in Q for the change in Z across this element, which results in what? Clockwise or counterclockwise rotation? Clockwise, right? So, but we know that positive curl is counterclockwise, right? Counterclockwise. So that's why when we get to the formula, we're actually going to subtract the partial of Q with respect to Z as its contribution to counterclockwise rotation. So it's all the same stuff we did before. So that's what we just talked about, that how much Q changes for a change in Z is the rate of change of Q with respect to Z, and how much R changes. So that's the red ones, right? The red ones here. How much does R change with respect to Y? So what is dr? So dr is what? Is it up or down? Dr. The way I've drawn it. With these two examples, this example. Up, because this one is bigger than this one, right? So dr is like a little vector up. It's how much greater this r sub right is than r sub left, right? Is dr. And so is that contributing to clockwise or counterclockwise rotation as we increase y? Counterclockwise, right? So as we increase y, how much bigger this one is than that is going to cause counterclockwise rotation. So we want dr dy has a positive contribution to counterclockwise rotation. Are you following this? So that's why we want the positive contribution of dr with respect to z. Did I have this messed up? No, with respect to y. That's right, with respect to y. So as we increase y, a positive dr is going to make counterclockwise rotation, so that's positive. But as we increase z, a positive dq makes clockwise rotation, so we need to subtract that. So this then is one of three contributions to rotation in R3, right? It's the rotation specifically in the YZ plane, right? The YZ plane. We already talked about in the XY plane, and then XZ plane, we're not going to go through the whole thing again, would be that we go through the same analysis here and get what the contribution of rotation in the XZ plane is. Okay, so this thing, curl, so for instance, for a change in Z, we use what part of these vectors, right? So thinking about, back to the beginning of the course, for a change in Z, this vertical change right here, what matters from these vectors here for a vertical change? The horizontal component. Does that ring a bell at all? Does that ring a bell? So we want what? We want the part of this, we want the part of these, the change in these vectors that are what? Orthogonal to the direction we're going to see the change. What is that? Does that remind you of anything? What's that? Cross product, right? It's cross product. Okay? So we want the amount of the change in FB and FT in as much as it's orthogonal to our change of DZ. Okay, so that's why curl is based on, calculating curl is based on cross product. Because we always want the orthogonal components to our change in location. That's what gives us rotation, right? Should make sense. Okay, so we have this, so that's why it's based on cross product. So there's this thing called, this is our, I want to call it the gradient operator. And it's kind of like a ghost vector, right? It's because it's not really it's not values or expressions, but just operations, right? So this is this right here, this middle line here, is what we call the gradient operator. And so since curl is cross product, you can calculate it using our cross product algorithm with I, j, and k as the first row, and this kind of ghost vector, this gradient operator as the second, and then p, q, and r as the third row. And then we follow how we learned to do cross product before as what the determinant of the 3 by 3. Do you remember that? So if we follow that algorithm, but not doing multiplication, instead of doing multiplication, we're thinking about these operating on p, q, and r as we do the algorithm. So for instance, so the I component would be what? It would be the partial of r with respect to y, and then thinking about another I here, and then the partial of what?
Z or Q.
Q with respect to z. So we get what? R, y minus qz. I think that was the one that we did. Is that the one we just did? Yeah, in the x direction, right? YZ plane. So that's the YZ rotation. And then we said that the direction then is orthogonal, right? Orthogonal to the plane of rotation. And so now the j component would be what? This is the one we didn't do, right? And the x rotation in the xz plane would be what? Going down this way? P with respect to z, what? Minus. So that's the one we didn't do, but we could do it, and it's all the same. And then finally, the first one we did, which is xy plane, would be the familiar one, right? Q with respect to x minus. Okay. So to get the overall rotational rate of change in R3, you're going to add up these three components. The rotational rate in the xy plane, that's the last one. The rotational rate in the yz plane, that's the first one. And the rotational rate in the xz plane, which is the one in the middle. And that will give us, when you add them together, you get the combined effect, the rotational rate at any given point. So that's the curl of F. And so what do we get? We get, when we do all that math, we just get a single vector, right? Just a vector like this, okay? Which tells us the overall rotation is in the plane orthogonal to whatever that vector turns out to be. That's how it's rotating. And then the magnitude, so the magnitude of the curl is the rate of change. So that's just a scalar, right? And then the direction is orthogonal to whatever the plane of rotation is. So the direction of the curl is the direction of that vector that you get. Okay, really important here that curl is a function, okay? What does that mean? Rotational rate or curl, it's a point-wise phenomenon, so make sure your brain is on. Don't just copy words, okay? rotational rate is a point-wise phenomenon, meaning it varies depending on the point you are at the field, right? So as the field changes, curl changes. So it's a point-wise phenomenon. When you talk about curl, you're talking about rotation at a given point. And then you get a whole function of that, right? That's the curl function is given location, what's the curl at that point? Given location, what's the curl at that point? Given a location, what's the curl at that point? Okay, so let's do some examples of curl. There we go. Let's do this one first. My favorite. So here, we'll just do examples in XY plane to make it easier, just conceptually. So here is a vector field. Is the curl positive or negative? Is the curl positive or negative? Positive. Because? It's going counterclockwise. Okay, so let's kind of dive in and investigate that a little further. So I want to take a point right here. And let's look at changing, so this is x and y. So we're going to look at changing x and changing y and seeing what happens here, say at this point right here. Okay, so if I'm changing x, what components of these vectors do I care about if I'm thinking about a change in x? Vertical components, right? Y components. So I'll do those in black, say. So for a change in x, what happens to the change in f? So it's this point right here.
It's a negative change.
The vector is getting shorter, right? So what kind of rotation does this indicate as I'm moving this way in x? My vertical vector just got smaller. Does that indicate clockwise or counterclockwise rotation? This one's bigger than this one. Is that going to be clockwise or counterclockwise? Clockwise, right? That's clockwise rotation from that. All right, let's look at the vertical. So so for a change in y, I'm interested in what components of these vectors? Horizontal, x component. And what's happening to those? So let's look down here. What's going on here? That's not right. So look up here. So what about, so these vectors here are as we go north here. What's happening to those x components of those vectors as we head north? Getting smaller. What does that indicate? Clockwise or counterclockwise rotation? Clockwise. So what is this? Q dx. You told me is clockwise rotation, and this is also clockwise. But I thought you told me this was positive curl.
Just at that point. At the center.
So what's the moral here? Curl is pointwise thing. So look, this whole thing is, as whole thing rotates, what? Counterclockwise? The curl is actually, so one way you can think about this is think about this as a flow field, like a whirlpool. And we've got a little flywheel in here that's allowed to move and rotate. Okay, it's just allowed to move freely and rotate. Which way is it moving? Counterclockwise. Does that mean the curl is counterclockwise? No. What do we look at to see about the curl? how it rotates as it moves. It's going to move around like this, but what it's going to do, based on our analysis here, is it's going to turn this way. It's going to turn clockwise. Locally, it's going to turn clockwise as it's moving counterclockwise. So curl is positive or negative?
Negative.
Okay? So just reiterates the point that curl is a local phenomenon. It's a point-wise phenomenon. It's not a global phenomenon, right? So you can have this flywheel going around in a counterclockwise circle, but turning clockwise as it does it, and that's what matters for the curl. Pretty cool, huh? All right, how about this one? So is the curl positive or negative? So because it's moving, what? Because it's moving clockwise, it must be turning counterclockwise?
Counterclockwise, but it gets bigger as you get away, which is the opposite of last time.
So let's do, on this one, let's do the math, okay? Here's the vector field. The vector field is negative y over x squared. And I actually have it as a R3, so we can practice. So, a negative y, x to the minus 2, x to the minus 1, and 0. So I'm going to practice computing the curl using the algorithm, right? So what do? We're going to do the determinant of ijk. And this is partial respect to x, partial respect to y, partial respect to z. And then we can fill in our particular components here. And then do the math. And we're going to get a vector function, right? We're going to get a new vector function, which is the curl. Andrew? Because?
Because you end up in classifying the derivative 0 for ry.
Yep.
And then q in terms of z is also 0 because there's no z component.
Right. Partial of x to the minus 1 to the z is 0. So I did the generic case and I wrote out the formula, but I think when you're computing the curl, it's just easiest just to go back and do this every time. It just makes it easy rather than, then you don't have to memorize anything, right? You don't have to remember it. You just know that you're going to do partial with respect to x, y, z, write out your vector field, and then do your algorithm like this. Okay, so then what about the y component of the curl? Did you get it?
Got 0.
0 again, because the partial of z, this with respect to z is 0, and then 0. Okay, and what about the z component? Partial of x with respect to x to the minus 1 is negative 1 over x squared. Minus partial of this with respect to y. Nope. With respect to y. And so we get conclusion? The field is called irrotational. Meaning, this field has no pointwise rotation anywhere. Yes, the whole thing swirls as a big whirlpool, but pointwise, there's no rotation anywhere. Okay, what did it mean? Do you remember what it meant when qx minus py was 0? Conservative. Irrotational vector fields are conservative. Or which is the other way around. Conservative vector fields are irrotational. If it's a conservative vector field, there's no, the rotational rate of change at any point is 0. meaning there's no effective rotation at any point. Does that make sense? Okay, we need to move on to the other type of rate of change in a vector field. So this is only half of the story, but the other half is easier. Okay, this is the harder half. Okay, so the rotational rate of change of a vector field is called curl, and that's a vector, right? The direction of the vector is orthogonal to the plane of rotation, and the magnitude of the curl is the rate of change, the rotational rate of change. Any questions on curl? All right, so let's talk about the other one. Divergence. So divergence is the other kind of rate of change that you have in a vector field, and that's a matter of expansion and contraction. At what rate is the field expanding or contracting? Again, as a point-wise phenomenon, location-wise, okay? So again, we're going to investigate one small element, and we'll just do dx dy. So we're in the xy plane, and I've got my 4 vectors. Same thing again. So thinking about a change in y, or we'll start with change in x. Thinking about a change in x would be the change in this vector to this vector. What's going to contribute to expansion and contraction for a change in x? For a horizontal change across this element, what's going to contribute to the x components, right? The x components are going to be like pushing and pulling as for a change in x, right? And then what about for a change in y? The y components, right? So now this is easier because everything matches up. When you change x, what contributes to expansion and contraction is the x components. When you change y, what contributes is the y components. So we don't want those, right? And we don't want those, right? Okay, so then for a change in x, we care about the change in p. That's the purple ones. And that rate of change is just the partial of p with respect to x. And for a change in y, for the dy, the vertical change, we care about the parts of the vectors in that direction. We care about partial q with respect to y. So then in R3, so we can just jump right to R3 here and say that the total expansion, the total rate of expansion, is just going to be the sum of the expansion in the x direction and the y direction and the z direction. So it's just going to be that. So it's easy. It's much easier than curl. And so what is that when we want the part of the vector in the same direction? What is that? Right. So we want the amount of a vector in as much as in the same direction. That's what we got here. So this is called the divergence of F. So how are we going to use the gradient operator on the vector field on P, Q, and R? We're going to dot it, right? We're going to dot it because we want the amount of these vectors P, Q, and R in as much as they're in the direction of X, Y, and Z, respectively. So we're going to use the dot product. And so you see that if you do the dot product on this, right here, you get exactly that. Just the sum of the 3 partial derivatives in their respective directions. So is divergence a scalar or a vector? It's just an amount, right? The amount of expansion or contraction doesn't have direction on it the way that curl does, right? Curl has a rotation, and so then there's a plane of rotation, and so there are directions orthogonal to that. But expansion, the rate of change of expansion, is just how much, at what rate is it expanding out or contracting in? And it's just computed by the individual, adding up the individual 3 components in the 3 directions. Okay, so let's look back at those. Let's look at the second example we did for this one. So I want you to go ahead and, well, let's start at predict first. So here up here, so if I pick a point, say right there, and I'm thinking about changes in x, am I going to be looking at, for change in x, I'm going to be looking at horizontal or vertical components of the vectors for divergence? Horizontal, okay. So notice we're moving to the, what? moving to the left. So as things move to the left, is there expansion or contraction? Expansion, right? So in the x direction, it looks like what? Px is positive, right? And then in the y direction, blue, which direction are we moving? And what about that? Do you see? So this is, and then we're looking at qy. So you see, what's that? It looks like it's about 0, right? So therefore, in the first quadrant, what do we think that divergence is?
Positive.
Positive, right? Because you have a positive contribution from moving left and right, and up and down. It looks like it's kind of staying the same. So we would suspect that in the first quadrant, divergence is 0. All right, let's go over here to the second quadrant. I'll do attendance now. I'll let you work on the other 3 quadrants. So look at this quadrant, and this quadrant, and see if you can eyeball what you think Px is and what Qy is in each quadrant. Rather than talk through all that, so what did you guys come up with? Just instead of, did anyone come up with the second quadrant? What do you think? Negative? That's what I'm hearing. Does that agree with that? Third quadrant? Positive? Fourth quadrant? Okay, good. You guys have consensus? So now, prove it. Prove all this guesswork that we did. This is the same one we did for the second one for curl. Right? Do you have that? What vector field is this?
Negative 1 over x squared.
Okay. So prove your hypothesis here that its divergence is positive in the first and fourth quadrants and negative in the second and first and third positive. Second and fourth quadrants, it's negative. Prove it. How would you do that? Do it. What was the original vector field? Do you have it written down?
Yeah, negative y over x squared. 1 over x.
Okay, so what's the partial of this with respect to x?
2y x.
2y over x cubed. Partial of this with respect to y? 0 and 0. So, in the first quadrant, x and y are both positive. So we'll get, oh, so this is not a vector. Sorry, guys. Told you. Plus. Okay, so in this first quadrant, both are positive. So we get, for the divergence, we get positive. In the second quadrant, y is positive, x is negative, a negative cubed will also be negative, so you see this is negative. So you see it follows. And when both are negative in the third quadrant, this will be negative. When x is positive and y is negative, this will be negative. So if you were able to eyeball those positive and negative of the divergence, then this proves it. That in the first and third quadrants, divergence is positive. In the second and fourth quadrants, divergence is negative. Okay. So, because vector fields are more complicated beasts, they have 2 rates of change, right? They have a rotational rate, which is a vector, the curl, and they have expansion contraction rate, which is the divergence, and that's a scalar, and that's a scalar function, right? So again, curl is a vector function. Meaning you get a vector depending on location. Divergence of F You get a scalar, but it's a scalar function. Again, it's just a number, but it's a number depending on your location. And in this, for example, here you have expansion in the first and third quadrants of this example, but you have contraction because you have negative divergence in the second and fourth quadrants. Okay, questions on that? Yes, please.
Could you possibly rationalize that by seeing how the vectors in the first quadrant are pointing, almost like they're pushing into the second quadrant, whereas there isn't much material going in, or is that?
But that's global thinking, right? Just because it's pushing that way or pushing this way, that could be expansion or contraction depending on relative size of the vectors pointwise. So it just goes back to that first example that I showed you, that first curl example. The whole thing is going one way, but pointwise it's going the other, and that's what matters. So the same thing with divergence. The whole thing could be, so you can have a vector field where everything's moving to the origin, but the divergence is positive everywhere, right? You would think if it's all moving toward the origin, that it'd be contracting, right? But you can have it so that everything's moving towards the origin, but that the divergence is positive everywhere. In fact, it's expanding everywhere. Same thing. If you can have something moving away from the origin, but negative divergence, contracting everywhere. Okay, yeah.
So we interpreted curl being 0 as meaning like there's no rotation. So what does it mean if the divergence is 0?
So the divergence is 0 means there's no expansion or contraction at any point. So there could be movement, there could be rotation, but there's no tendency of expanding at a point or contracting at a point. So I think there might be a term. Incompressible, that's what it is. So divergence is 0. Thank you for bringing that. If divergence is 0, that's called incompressible. But that does not relate to whether the field is conservative or not. Okay? Irrotation, so the curl being 0 has that relationship with the conservative vector field. But whether a field is incompressible or not is not related to conservative, whether the vector field is conservative or not. Okay, thanks, good question. Please.
So in the first quadrant, we said that in the negative x direction, the expansion is positive.
Right. So you just to analyze divergence, you look at which direction things are moving, and if they're expanding in that direction, you have positive divergence. If they're contracting in that direction of motion, then you have negative divergence.
Okay. So you wouldn't say that in the positive x direction, expansion is negative.
So there's like a double negative, right? So in the positive x direction, your vectors are getting smaller, but in the opposite direction. So you get a double negative, and it's still positive divergence. That's why it's just easier to think. Just drop a flywheel in there and just let it move, and then in that direction, analyze whether things are expanding or contracting, and then you don't have to worry about
So for divergence, unlike curl, where you do like counterclockwise, you make the positive. This one is just whichever is in the direction of motion. So if this was like, let's say all the vectors were opposite, so it was going clockwise instead of like counterclockwise. Would you look at like the positive x direction?
So we could do it by looking at the positive x direction. It's just it's a little more confusing. So always looking in the direction of motion when thinking about divergence is just the easiest way to do it. But if we were looking in the positive, so for a dx this way, what's happening? Getting less negative, right? So the change in Q is negative and getting less negative. So things that are getting less negative are increasing. Therefore, divergence is positive. So that has the same effect as saying, oh, we're moving this way. Whatever point in the field is moving this way, and things are opening up as in the direction that we're moving. So that's positive divergence. So that's just an easier way to see it. But yes, you could say just dx for positive change in x. Those vectors are getting less negative, therefore positive change. Does that answer it?
Yeah.
Okay. All right. So call it there. So. Look on Blackboard for all the work you have to do, but get ready, it's going to get hard next week.